In this and also in the next learning sequence, we are going to talk about principal component analysis, probably the most famous method in this course. And if you, for example, if I have to select the most important lecture in this course, that probably would be the one, the most important one. Okay. So that's the plan. First of all, we will start from just some general things, define latent variables and projections, then talk about how to actually what principal components are, how principal component analysis works. We will discuss also one of the algorithms that is used to find principal components. And then finally, talk a little bit about how to interpret PCA results. So let's talk about latent variables and projections. First of all, I would like to remind you one of the slides from the previous learning sequence. You remember the problem is that when we have a lot of different variables, when we measure a lot of different factors, then it's difficult to visualize interaction between these factors because you have too many combinations. For example, if you have only two variables, then you can easily visualize interaction by making a scatter plot like I did here, right? It's not fully a scatter plot, of course, but just a kind of. But if you have, for example, three variables, then you need to have, you actually have three pairs, right? So it means that you have to look at three plots and then calculate, for example, three correlation coefficients, right? And then if you have 10 variables, then your number is 45. So you need to look at the 45 plots and calculate 45 correlation coefficients, which is quite a lot, right? And then if you have 100 variables or 1000 variables, it's insane. So what to do? The idea is following. If we have too many variables, let's reduce them. So let's change the number of variables from too many to few, or not too few, just few. The idea is that very often, we can do that without actually compromising the quality of the representation of your data values. And that is done via latent variables. So what is the idea? The idea is that we can find a very small number of variables which can describe all your data variation almost as good as your original variables. And then if you indeed can do that, you can project your data points from highly dimensional space to this lower dimensional space. Okay, and then you use lower dimensional space instead of the original one. So that's the overall idea, and actually most of the methods we are going to talk about in this course starting from now somehow utilize this idea. The problem is how to find this subspace, how to find these latent variables. Well, this subspace is defined, as I already said, by these hidden variables. We are going to talk them latent variables. So latent variables is just access and variable space. And the idea is that this access, these new variables, are selected to make representation of your data structure as good as possible, right? As efficient as possible. And then any method that we are going to talk about in this course starting from now can be described by three steps. First of all, you need to find the latent variables that fits the problem you want to solve, and then project all objects to latent variable space, and then use projections instead of the original data. This is a very simplified version, but still. Now, by doing that, you actually split your data into structure and noise. Structure is what latent variables explain, so this is the variation that can actually be described by latent variables, and noise is everything else, okay? And then data is your original data. If you remember applied statistics, if you remember, for example, analysis of variance, ANOVA, this is exactly what we do with ANOVA, right? So we also split your data into structural part, it's the variation of mean values, and noise, it's the rest. It's a variation within the groups and so on. So actually this is a very common approach, splitting your data to structure and noise. So let's see how actually PCA does this. But before, let me just again give you some general concepts. So first of all, imagine that we have data like this. So it means that we have two-dimensional case, we have two variables. In this case, I have just abstract variables x and y. You can think about anything like height and weight or any other two variables that have a good correlation like we observe here. And then let's say I have like 20 data points here or similar, and then it means that I have 40 values, right? Two variables, it means two values for each data point. What if I don't have enough space in my computer memory to keep all these 40 variables? Well, I can do only 20. Can I reduce the number of values from 40 values, of course, from 40 to 20 without actually almost compromising the quality of representation of my data. So in this case, I can find a latent variable which actually is oriented along the biggest spread of the data, right? So I know this is the biggest spread of my data, this is the direction of the biggest spread. And if I take this as a new axis, so this is the latent variable, right? And project all my points to this latent variable. So I will get, you can see that, for example, I have blue points instead of these two gray points, right? I will solve the problem. Will I lose anything? Yes, I will, because look at this one. You can see that the original position of the point is here, but the new position is here. So this little distance between these 2 points, it's this residual variance. It's something that I cannot explain. I cannot explain this one. I cannot explain this one. I cannot explain this one. But if you look, if you compare what we can explain with what we cannot explain, you can see that the ratio is pretty small. We explain most of the variation. Moreover, you can see, for example, these 2 points, right? This is the original, these 2 points are close to each other, but projected points are also close to each other. Yes, the distance between 2 points is getting smaller, but very little. So of course we lose something. It's not possible to reduce variables and without losing anything. But the point is that we lose very little. Moreover, you can see that this is a kind of trend in this direction, right? So this variation looks more random, and therefore we can say, okay, that's noise. That's something that is not related to the effect we want to actually to deal with. Okay. So this is one of the examples of using these latent variables plus projections. And in this case, we indeed reduce the dimension of our data actually twice, right? So because if you think about the new plot here, you can see that the coordinates of blue points can be described along this red line. So it's only one coordinate, right? Then we keep the important data structure, and actually we keep it very well. So we explain most of the variance of the original data points. And then the unexplained variation, this little fluctuation around this line, we consider as noise. And noise means it can be real noise, it can be anything that is not relevant to our problem. Okay, so this is how it works. Now let me show you another case. So this is my new data, and then in this case, let's say we have another task. If you can look at these points, you can see that actually we have like 2 groups of points, right? So this is group number 1, and this is group number 2. What if the task in this case is to separate the groups? The task is to see which group a point actually is from. Can we, in this case, reduce number of variables from 2 to 1? So it means that we will actually reduce the dimension of our data. We will have twice less values. We will have twice less values, but at the same time we keep the most important structure. What it means that we still keep these 2 groups of points separated. So in this case, the task is not to explain the variation. The task is explain the difference between the 2 groups. And indeed we can do that, but in this case the orientation of latent variable will be a bit different, this one. You can see that we lose a lot of information. We lose all these fluctuations, all these variations, right? But we don't care. For this particular task, all this variation that we lose, it's noise. Why? Because it doesn't help us to see the difference between the 2 groups. Look how good the difference between these 2 groups for the projected points, right? We actually even underline the difference by doing this projection. So again, we do the same things. We reduce the dimension twice, and we keep the most important data structure very well. And then what is not explained by our latent variables is noise. And noise in this case is not the real noise. It's a unrelated information. It's a variation of our data which is not related to separation between 2 groups. Okay. Then I can continue with these examples, but I think that you can see already the overall idea. You need to find latent variables that capture variation of your data, which is important for this particular task, for the task you are working with. It can be explaining the variation, it can be underlying the difference between groups, it can be anything else, but the orientation of latent variables should be selected depending on the case, depending on the task you are going to solve. Okay. So that's actually it. By once again, the overall idea is to split data into what is relevant and what is not relevant to your task. And then what is relevant, we call it a structure. What is not relevant, we call it a noise. And then noise can be the real noise. Noise can be as just a non-relevant information. We will just call it a noise here, right? So that's the concept. And now let's talk about how actually principal component analysis utilizes this concept.